we are going to go over a not an arrow pushing exercise for resonance structures, not an actual reaction, right? So these are not reactions. These are just ways we can draw different forms of molecules. All right, so this is an example from our homework.
You don't have the screen.
So an example from our homework.
Oh, I can't today though.
So this is something called an isocyanate. Don't worry about that, but a little bit of extra knowledge for you guys. So, a couple questions. What's the hybridization state of this carbon?
sp2.
How many pi bonds does it have?
2.
So it has to be what hybrid? So how many p orbitals must it have to have 2 pi bonds? 2. So what hybridization state must it be? It's sp. It's sp.
That's a trick question.
I don't know if it's really a trick. You have lone pairs, pi bonds, and lone pairs. So for resonance structures, the only things you can move are lone pairs and pi bonds. And you can only move them towards sp2 or sp hybridized elements. Right? I could not move these electrons this way. Right? I can't move these electrons this way. Why can I not? Because this carbon's what hybridization state? sp3. We do not move electrons towards sp3 hybridized elements. But we can move them towards sp2 or sp hybridized. So what happens here, how do we do that? So what are they saying? They're saying draw the predominant structures. So what you can do is, I can move this lone pair, this nitrogen lone pair, and it's going to form another pi bond. But if I make a bond, I need to break a bond. But this is not a reaction. Realize that. Please realize this is not a reaction, right? We're just moving electrons within one molecule, just showing how different ways this molecule can basically behave or react. So this didn't change, so that stays there. Now, in the beginning part, I had no charges. Where should there be a plus charge at? The nitrogen should have a plus charge, right? Because now it has 4 bonds. What about the carbon? Does the carbon have a charge? Nope. What about the oxygen? Does the oxygen have a charge? Has to be a minus, right? Because, remember our 12 rules we were given. Right? One of the rules is we cannot lose, right, electrons. We have to balance our charges. So initially, if we have no charge, in the products, or in the resonance structures, not the products, the resonance structures, you also must have no charge. Okay, so let's look at a retrosynthetic problem from our workshop. So, if you look at this basic analysis, what are we looking for? The first thing I would say is how many new carbons do we add, or how many carbons do we add? So we start out with 2 carbons, and how many do we end up with? 1, 2, 3, 4, 5. So we have to add 3 more carbons, right? So maybe put yourself a little note, say 3 C's added, right? And we only know the only way to do that, right? The only way we know how to do that is with what? What does the starting material have to be for that? Has to be. We have to use a sodium, strong base, and we need to use alkynes, right? So usually when the first things we have to do is add the carbons. Right? So that's one point. What's the other thing that's new here? What else does the product have? It has a ketone. So we have to think about the ways we make ketones and what they come from. What do ketones come from? What kind of starting materials? They come from enols, and enols come from alkynes. Right? We make alkyne from alkynes. We make ketones. Right? So that's just kind of initial analysis. Just look at it and say, okay, before you even start worrying about anything else, let's do that. Now let's start working backwards. First thing I would do is number the carbons in the product. 1, 2, 3, 4, and 5. Right? Now, there's more than one way to do this, actually. There's like actually a couple ways. But this, we only get one ketone. So if we only get one ketone, what kind of star material does this come from? A terminal alkyne. All right, so where would the alkyne be at? Between which two carbons here? Do you see that? The carbon between 4 and 5 has the alkyne.
So if there was more than one product, you'd give us that?
I would. All right. Always be careful with our alkynes, how we draw them, remember? 1, 2, 3, 4, 5. Don't forget our bond angles that happen with alkynes. Okay, from this point, we have a terminal alkyne. Could we have made this terminal alkyne from the starting material? Yes, we could have. So that's the retrosynthetic way to do it. Notice the arrows, right? The retrosynthetic arrows are different. Now let's do the forward synthesis. So what actual reagents do we need to make this, get this accomplished? So to add carbons, we always use, first thing we use is Na, NH2, that strong base. And part 2, we need to add an electrophile. How many carbons do we need to add? 3. So we need to add a 3-carbon piece with, say, a bromine on the end. Right? So if we number this, we say 4, or yeah, it's 5. Do we need to include how many equivalences of NaNH2 we use?
Yes.
Yeah, we probably should. Probably should say something about 1 equivalent. Right? And that'll give us this product, which we wanted. Right? If we say, which carbon formed a bond? So be careful that carbon 3 is the one that's going to get attacked by carbon 4. Carbon 4 is going to have the negative charge, right? NH2 minus is going to deprotonate carbon 4. It's going to C minus here in an sp orbital. That's going to attack carbon 3 and break the carbon-bromine bond. Right? Everybody see that? Yep, Lucy.
This might be a stupid question, but how do you know if you have more than one equivalent of like the NaNH?
So I only say 1 because I only want to add carbons on one side of the alkyne. So I say 1
If
equivalent.
there was like 2 carbons added to like
If I wanted,
5, it would be 2 equivalents then?
if it was, well, if I wanted to do 2 steps then.
Okay.
Yeah, if I wanted to, now if I got to this point and I wanted to add more carbons over here, I would do this again with a different thing. Yep.
For
Good.
step 2, do you need to do that too, or?
No, so for step 2, let's look at step 2. So what do we need for step 2?
No, I
Well-
mean like the.
Oh, just the one, you can use an excess, it's fine. For step 2.
Okay.
I mean, 1 equivalent should be fine too. So now for this last step, to turn a terminal alkyne into a ketone, what reagents do we need?
H2SO4.
We need H plus, water, and remember mercury 2 plus. We need mercury 2 plus to do that. Remember that forms the mercurium ion, then the water attacks, and we go through this whole process of losing the mercury. Okay, so let's try one with a terminal alkyne with Hg2 plus, H plus, and water. So first thing we do, number of carbons, 1, 2, 3, and 4. We always want to find the best electrophile. Right, so which is the best electrophile do you guys think here?
Hg2 plus.
Right, Hg2 plus, right? Instead of just H plus, Hg2 plus is probably the best electrophile. So what happens is the pi bond attacks at the same time, the Hg comes back and attacks again. And we form a mercurium ion. Something like this. So this is very similar to the bromonium ions we've done with, or chloronium ions we've done. The same rules apply as well. So which carbon should we attack if we had 1, 2, 3, and 4? Which carbon is most likely to get attacked by the nucleophile?
3.
Carbon 3 because it's the most substituted. It can stabilize the positive charge the best. So that's what we have attack. We break this carbon-mercury bond. Now it should be what kind of product should we get? Trans, good. All right, should be a trans product. Be with me so far? 1, 2, 3, 4. Alright, so the first step, we'll just lose the H, and that'll get us this product, this initial product, which is what? What do we call this guy? An enol, good. Right? And enols can tautomerize into what? Ketones. The problem here is our mercury is still on here, right? Alkyl mercuries will kill you. Bad deal. No, we don't want that. So we need to get the mercury, break that carbon-mercury bond, essentially. So one of the ways, so you should know how to do this mechanism too. And don't forget, you need to know how to do this. Tautomerization. But I'm going to show how we get rid of the mercury. Essentially, there's still H plus floating around.
What is that? Is that saying trans?
Tautomerization. Tautomerization. Right, so H plus is around, so the pi bond attacks H plus, the mercury leaves and forms a new pi bond, right? Number of carbons 1, 2, 3, and 4. So now there's a new pi bond between which two carbons? 3 and 4. Mercury's gone. And we've remade what? The enol, which of course can tautomerize back into a ketone. Yes? Do you understand the mechanism for tautomerization? Should I do that quick? Let me do it? I'll do it. Why not? You only live YOLO. Oh, God. Are we recording? So you can do this a couple ways. You can say these two electrons left and this pi bond attacked, and that's how we get to that tautomerization. So you'd form a pi bond between oxygen and carbon 3. All right, these electrons move here, new pi bond. This pi bond attacks, we form a new CH bond on carbon 4. That's the tautomerization.
So what happens to the H?
Yep, the H here regenerates H plus as a catalyst. This H is now this H. See how it lost the 2 electrons?